Okay, let's do some math for fun. Here we're going to integrate 1 over x to the fourth power plus 1. But in this video, we are going to integrate it from 1 to infinity. Yes, I did this integral last year already by using like some hardcore partial fractions. So if you haven't seen that video, please go check that out. Today, we are going to do it slightly differently. Recently, we did a video on the integral of this following integral. So let me just put this down. The integral of x squared plus 1 over x to the fourth power plus 1 dx. And that was a lot of fun. Not as fun as the hardcore partial fraction, but you know, it's also pretty good. And in fact, we can actually use this idea to do that integral. And then in the end, of course, we have the 1 to infinity. And this is also a famous step when you want to integrate square root of tangent x. Once again, I will have a link in the description for you guys if you haven't seen those videos. All right. So, my first step is that I will see how I can make this into this kind of form. Let's see if I can make that happen. All right, first of all, this is still the integral, and perhaps I just put this down. We have x to the fourth power plus 1, and we have the 1 right here. So this is good. And of course, this is going from 1 to infinity. Now, I need to get the x squared. It's okay. I will just add the x squared. So let me just put this down. I have the x squared. But of course, I cannot just put on the x squared, and that was a positive 1. I will have to subtract the x squared. Otherwise, I'm just like making things up, right? So I have to minus x squared. So this is good, right? This is still equivalent to the original. And I'm going to separate them, so I'll just put this down as this over the same denominator, of course, which is x to the fourth power plus 1, like that. All right, so this is good. I can integrate this guy. But to integrate just x squared on the top over x to the fourth power plus 1, this is pretty difficult, almost as difficult as the original. In fact, as I said, I want to deal with this kind of integral. I want to have a plus 1 right here to help me out. But if you just put down plus 1 right here, what happens? Look, this is x squared plus 1 minus x squared plus 1. We have just a 0 inside. So we're just integrating 0. That's not possible. That's no good, right? No, we're making things up. Therefore, in order for me to have a 1 to help me out, I will just say let's minus 1 instead. Yeah? So as you can see, this form and that form are similar now, and we can approach it by the same strategy. Well, so what kind of math have I done? Let's see. X squared minus x squared, that's good, that's 0. So that's okay. But 1 minus negative 1 is positive 2. Originally, I have 1. It's okay. Let's just multiply by 1/2 all the way in the front so that we can pretend nothing happened. So this is good. This is the massage that we have to do to change that integral to the forms that we like, right? And as I said, we'll pretty much use the same strategy like last time. Like a few days ago, I will just go ahead and multiply this by 1 over x squared. Likewise, I'll do it on the bottom as well. And let's also do this, multiply this by 1 over x squared. Okay, so that's really cool. And then, let's see. Right here, perhaps I'm going to just look at the first integral from 1 to infinity. And for the top right here, we will just have 1 and then plus 1 over x squared over. Now, when you have this, you get x squared plus 1 over x squared. Well, let's take a look right here. Another thing that we know, right? Perhaps I should put on notes, but it's okay. Right here, we pretty much will get x squared and then plus 1 over x squared, isn't it? Yes, it is. And just like last time, perhaps we can review this again if you haven't seen the recent video. What we are going to do is we're actually going to complete the square in the following way. I will show you, don't worry. First, you see that this right here, this is like saying a squared plus b squared. But I want to have a squared either plus 2ab or minus 2ab in between, and then plus b squared at the end, so I can factor that. This right here, I cannot factor at the moment, and we keep everything real in this video, of course. So this is what I will do. Let's look at this as x squared, leave a space, and then I will add it with 1 over x squared like this. And in the middle, it seems that we have two choices. We can either add or subtract 2 times this and that. Maybe you're not sure which one is which. Let me just write it down for you guys. Perhaps I can say that's minus 2 times x times that, which is 1 over x. When you do that, well, you will have to add this back, which is plus 2 times x times 1 over x, so that this and that are still the same. And then, from the first 3 terms, we can actually factor this. We get x minus 1 over x squared, and this right here is, of course, just plus 2, right? X cancel. This right here, it's pretty much that. It's the same as the original denominator. And it depends on what kind of thing you have on the numerator. This right here, if you put this down, this is perfect because you can just do a little u sub. Because if you differentiate negative 1 over x, you do get positive 1 over x squared. And of course, the derivative of x is 1, so it matches out nicely. So this right here will go to the first denominator, and I will just write this down for you guys. Right here, x minus 1 over x squared plus 2, like that. And let's close this integral. And then we are going to minus 1/2. And then we have to integrate this from 1 to infinity. This guy right here on the top, we have 1 minus 1 over x squared over. When you work this out, you pretty much have this again. But I'm not going to put on the same thing. Instead, I will be looking at this as parentheses x squared and then plus 2 times x times 1 over x, and then plus 1 over x, and then square, and of course I add this, I will have to subtract 2x 1 over x, like this. And in this situation, if you add and then subtract like this, the first 3 terms, you can factor it. Well, it should be like this. Let me just do like this. This right here will give me x plus 1 over x, and then square, and then in the end, I minus the 2 right there. So this and that are really similar, but you have to pair things up nicely. I will use this for the new denominator right here. So let me write this down. I will tell you. You see, this is going to be x plus 1 over x inside, and you square that. And then you minus 2 after that. Now, from here, you can just do a little u sub. The derivative of x plus 1 over x is exactly that. So we are good. So this is pretty much it, right? Now, perhaps, let me just write this down for you guys right here first. Let's do a little u sub first. I will let u equal x minus 1 over x. And then, as I said, du will be 1 plus 1 over x squared, right? So let me just put this on right here, that u equal x minus 1 over x. And du will be 1 plus 1 over x squared dx. Similarly, right here, I will say, perhaps I'll use w. W equals this inside, which is x plus 1 over x, and then dw is equal to 1. And then differentiate this, you get minus 1 over x squared, and that's going to be the top as well, so that's good. Do this on, like, just, you'll see, let me see. Yeah. Now we have 1/2, and this is still the integral. The top right here is the du now, so just put down du in blue, right here on the side. And then we have 1 over u squared plus 2, like that. And then, of course, we have to go from 1 to infinity. And then we have to minus 1 over 2. Integral, this right here, it's the green one, so I'll just put down. And depends on how you want to do it, like seriously, okay? Yes, I noticed. This right here was x, going from 1 to infinity. So you should put down x equals 1. 1 minus 1 over 1, which is 0. So the u right here should be going from 0. And then if you plug in infinity into here, infinity minus 1 over infinity is 0, 0. So u also goes to infinity, right? All right, so this time x goes from 1 to infinity. When you put x right here, you get 1 plus 1 over 1, and w goes from 2, okay? W goes from 2. And then plug in infinity, you get infinity plus 1 over infinity, which is still infinity. That's good. On the top here, this is going to be dw. And let me just put it on the side. I will put on 1 over. And then this right here inside is the w, and then square. And then in this case, we minus 2 instead. And then the top is the dw, so we'll put it down on the side like that. Whew. Tired. Yeah, out of shape. All right, cool. So far, so good. Now we can totally integrate this guy, right? So for the first guy, this is going to be, when you integrate this, you will have to use arctangent, right? And you look at the 2 as square root of 2 squared. So let me put down the 1/2 first, and then I'll put down everything blue right here. The integral of this is going to be 1 over square root of 2, and then you multiply by inverse tangent, and this is the regular tangent situation, but it's still the inverse. It's the inverse, it's a regular inverse tangent. Here we go. And then the input right here, it's going to be from, well, it's u divided by square root of 2, like that, okay? And since we are in the u world already, let's finish everything in the u world. So I will go from 0 to infinity. And then to continue, we have the minus 1/2, and then we have to integrate 1 over w squared minus 2. Well, how can we do that? Well, let me put down more notes for you guys on the side. So here we go. Yes, you can use partial fractions, but let's not do that at all, okay? Recall that if you want to differentiate the inverse hyperbolic tangent, this right here, you do end up with 1 over 1 minus x squared, and this is legitimate, right? But there's a problem with this. Yes, I did use this last time in my square root of tangent x video, but that was because I didn't have the limits of integration. This right here, you have to do it carefully. This right here, it's only good if x is in between of -1 and 1. Why? Because this right here, it's a domain of the inverse hyperbolic tangent x. So at the moment, right here, I technically cannot do that. So does that mean I really have to do partial fractions? No, neither, because we have another one. Let's go ahead and look at the derivative of the inverse hyperbolic cotangent. Input, let's say it's x. This right here, the derivative of that, we still end up with 1 over 1 minus x squared. Yes, they do have the same derivative. This right here, it's good for if x is less than -1 or x is greater than +1. When x is 1, these two things are not good at all, but you have to pay attention to the domain. Therefore, pay attention to, we are going from 2 to infinity. So we will have to put down the inverse hyperbolic cotangent. And we also have to do some substitution, that kind of thing, because right here, we do have a 2, but it's similar to this and that. So you can do some u sub on your own, or maybe some whatever sub you want on your own. And of course, you see this is 1 minus x squared. Here we have the w squared minus 2. So instead of this minus, I will have to multiply this by negative, right? Therefore, in fact, I will end up with a plus right here. There we go. So this right here is a plus because we're minus, and this right here will give us the negative version of that. And then right here, if you integrate that, you are going to end up 1 over, look at the 2 as square root of 2 squared. So you have the square root of 2 right here. And then I'm going to use the inverse hyperbolic cotangent to help us out. And then it's pretty much similar to that. So you have the w inside divided by square root of 2. And you are going to go from 2 to infinity in this case. So this is actually what we have. We integrate this right here so nicely. And finally, we're just going to be plugging infinity, and that's technically you're taking the limit, and then you are just going to plug in the numbers and you're going to work it out. So for the first one though, let's do everything in blue here. When you plug in infinity here, you're pretty much looking at this as the inverse tangent of infinity, and that will give us pi over 2. Therefore, I will just write this down as 1/2 all the way in the front, and then we have the 1 over square root of 2. Plugging infinity right here, we get pi over 2. That's good. And then I shall be minus plugging 0. And the good thing is that the inverse tangent of 0 is 0. So it's pretty much subtract 0 like this. And that's pretty much it. And perhaps you can put on parentheses somewhere. Maybe I'll put on like that technically. And then we are going to add right here. This right here, we have the 1/2. And plugging infinity to here, let me just tell you guys that if you are doing the inverse hyperbolic cotangent of infinity, that will give you 0. Why? You guys can look at the graph of this. It's approaching 0. So the first part is actually going to be 0. And then you are going to minus, you have to plug in 2 into here. So I will just look at the green part, which is 1 over square root of 2. And then the inverse hyperbolic cotangent, and then you put down 2 over square root of 2 because you put the 2 right here. So that's pretty much it, right? Whew. And in the end, of course, if you want to do a few things to simplify this expression, yes, we should, and let's do it together. 2 times 2 is 4, and then we have pi and all that. So the first part we get pi over 4 square root of 2. That's good. Next, you have this times that, which is, that's a minus. So we have minus. And perhaps I can put this down on the top. So we put down the inverse hyperbolic cotangent. And 2 over square root of 2, it gives you square root of 2, right? So we're all dots, not just 2 on your own. And then over this times that. So it's 2 square root of 2. Like that! Oh my God. Finally, finish this right here. Alright, cool. So this is right here. It's how you can integrate 1 over x to the 4th power plus 1 by looking at what they call the algebraic twins. And you also have to be careful with when to use the inverse hyperbolic tangent and when you can use the inverse hyperbolic cotangent, depending on the domain, namely depending on the interval that you're integrating with. Alright, so this right here is it, and hopefully you guys will like this video. If you guys do, please give me a like. And if you guys are new to my channel, be sure to subscribe for more interesting math videos. And as always, that's it.
So good.